Okay, well, once again, Randolph, thanks for having me. It's always a pleasure to be here and share information with the audience. And, I think last time that we were here, we talked about insulation failures and some of the situations surrounding moisture in the insulation and the damages that it can that that can happen. Today, we're going to talk about mechanical failures, and it's a little bit different subject, but certainly just as important. A mechanical failure basically involves the physical displacement or damage of parts within a transformer. And, these can happen for several reasons. And probably the one we're most familiar with is transportation. When you purchase a new transformer, and especially if it's a large transformer and has to travel by rail or flatbed, it gets subjected to certain shock and vibrations. And this is, of course, one reason why we put vibration monitors on new transformers, especially if it's going by rail, where they're coupling and decoupling rail cars all the time, and it can certainly cause enough vibration on the transformer, enough shock to actually damage the internal windings of the transformer. But you have other causes as well. Seismic activity, earthquakes can create mechanical issues. Um, Improper synchronizing on a GSU can put a lot of mechanical forces through the transformer. But the one we want to focus on today, because I think it kind of gets overlooked in terms of in terms of being a diagnostic tool, and that is through faults. So if we look at a typical protective one-line diagram for a transformer, you'll see there's a number of different elements. You have elements such as the current differential, which is looking for faults internal to the transformer. You have some that are looking for to protect the transformer from outside influences, such as volts per hertz or whatever the case may be. But I kind of categorize protective elements on a transformer into two separate areas. One is proactive and one is reactive. So what do I mean by that? Well, a proactive protective element is something that would protect the transformer from damaging conditions that are outside the protective zone of the transformer itself, as opposed to reactive. Because if you have a true differential trip in a transformer, there's a good chance the damage has already been done. We don't know the extent of the damage or what the cause of the damage is, but that would be more of a reactive. And things like sudden pressure relays and buckles relays or things like that are really kind of a reactive protective element. And that's kind of the obvious, but I just wanted to point that out. But along with these protective elements, you have other things in the protective relay system of your transformer that can help as well. You always have the ability to look at metered values on the secondary side. In terms of having an event that actually happens, you have a sequence of events monitor that shows you the sequence of all the elements that may have reacted. Then you have your oscillography, which is important. But the one thing that people seem to overlook a lot, and that is the capability of your protective relay system to monitor through faults. And I had a good friend that I worked with at Schweitzer, from Schweitzer Engineering. We were doing presentations together, and I talked about through faults. And I asked him, I said, of your customers that you work with, how many of them do you find actually enable the through fault monitor on the relay itself? He says, shakes his head and goes, very few. And that really kind of surprises me. So in order to really understand what a through fault is, your power system faults are all external to the transformer zone that can cause high levels of current flowing through the transformers. Those through fault currents create forces on the transformer that can actually weaken the winding integrity. So a comprehensive transformer protection scheme needs to include protection against thermal overload. We know that. Overexcitation, problems with the windings internal to the transformer, but also for through faults. Okay, so you can see here in the graphs, these are some of the damages that you can see from either an excessive through faults or from a particularly strong through fault. So to understand a through fault, you have to know about differential differential protection and how it's used. You know, you have Kirchhoff's law where the current coming in equals the current going out. And if it doesn't, to a certain degree, that means that current is flowing into the fault, which means that you now have your differential is going to recognize that there's a problem internal to the transformer. But you can also have through faults will not affect the differential protection because it's the same amount of current that's flowing through the transformer, which could be much higher, okay, than the transformer is capable of withstanding. So you have to remember that differential protection will only sense the faults occurring inside the range of the two CTs that you see here in the diagram. And it's important to understand. So power transformers throughout the power system experience different levels of through faults. And these are in three particular terms. One is the magnitude, how high of through fault is going through the transformer. The duration, how long that through fault lasts, and then the frequency. So the recording capability of your transformer protection relays really can allow for monitoring and recording of through faults. Now, there are some transformer monitoring systems out there that can also do the same thing. Okay, but if you don't have a monitoring system that includes through faults, and it's funny because I was just recently on a working group for IEEE for the Transformers Committee that was updating the guide for transformer monitoring systems. And I came into the group a little bit late, and as I was reading through the entire uh, the entire program, there was nothing about through fault monitor. And I remember asking the chairman after the meeting was over, I said, you know, if we're talking about monitoring, why didn't you include through faults? And he kind of cocked his head and he goes, yeah, no, that's a really good question. And the only thing I could decipher was that transformer monitoring systems are looking at the health and the condition of the transformer. They're not concerned that they're not thinking about what's happening outside the zone of the transformer. So that could be one of the reasons, but these are the things that we really need to pay attention to. And if you see here on this diagram, you can have a through fault on either side of the transformer. Now, what could cause the magnitude and the duration and the number of occurrences? Well, there's a lot of things that can affect those three conditions. The one thing that I do want to point out, though, is that the potential damage to a transformer has a lot to do with the design of the transformer. So the path through which flux, and that's what we're talking about, flows makes the zero sequence impedance of a shell type transformer typically higher than that presented by a core form. So we know that through faults are more damaging to core form rather than shell form due to these multiple current paths that they have. Now, that does not mean that you could necessarily not have a damage on a shell form. It's just less likely. So through faults can really vary greatly across short spans of any electrical grid. This could be in a GSU. This could be on a EHV or high voltage transformer. It could also be happening in distribution. And in distribution, we know that if you see a large number of through faults, it could indicate that you've got tree limbs that are striking overhead lines. Down here in Florida, where I live, we're the lightning capital of the world, and lightning is certainly one of the things that can create a particularly large through fault on a transformer. Now, if you want to get more information in terms of the through fault, what through fault damage can occur, I'd recommend looking at C57109, and that is the IEEE guide for liquid filled transformers through fault current duration, and that kind of addresses the withstand capability of most of your modern transformers. So how do we set a through fault monitor? Well, ANSI and IEEE standards provide operating limits for power transformers, but initially these were all based on thermal effects on transformer overload. Well, lately the capability limit was changed to include the mechanical effect of high fault currents through the transformer as well. So power transformer through faults produce a physical force that will cause insulation compression, insulation wear, friction-induced displacement in the winding, and these effects are cumulative and should be considered over the life of the transformer. So if you were going to switch out a protective relay system that has, captured historical data on through faults, you want to apply that precondition to any new transformer protective relay that you're going to put on the system so you don't lose that information. So this table one, what we're looking at is, our transformers are divided into the 4 different categories based on the kVA rating, both single phase and 3-phase. So in setting a through fault monitor, you could have various different settings based on what category that you have. So if we look at a more comprehensive, representation of the long-term effects of the system conditions on transformers, each category includes through fault capability limits. Now, the best thing to do is refer to your transformer manufacturer to find out what those through fault limits are and use that information to decide how you're going to set that through fault monitor. So the maximum current in per unit value of the transformer base rating, and that's what we're looking at, the times number of base rating of the transformer itself, is based on the transformer's short circuit impedance for your category 1 and 2 transformers. Maximum current calculation for category 3 and 4 is based on the overall impedance, but also the transformer's short circuit impedance and the system impedance. What I would recommend highly is that in terms of setting a through fault monitor correctly would be to study the instruction manual that comes with the protective relay, as well as consulting your OEM on the transformer itself, and use that information to decipher. But what we're looking at here, and these are setting determinations right here, is you'll see on one section, this is your fault duration in terms of time and seconds, and then the magnitude in times base current. Okay, and you could see they look about the same. Actually, it looks like basically an overcurrent, inverse time characteristic of an overcurrent relay. And that's basically what we're looking at. The higher the magnitude of the through fault, the faster, the time in seconds establishes this curve. And you can see for categories 1 through 4, they look fairly similar. Okay, but they do differ slightly. And then, of course, you've got in distribution, you've got, well, I'm sorry, not in distribution, but in high voltage where you have a category 4, we want to coordinate with your time over current relay. So rely on your OEM to do this for you. So here's kind of what the logic looks like. The relay is recording a cumulative I squared T value for each phase and compares it against the threshold to provide an alarm. These recorded values could assist a substation crew in prioritizing transformer maintenance and testing. And we're going to talk about this a little bit longer because, one of the problems with monitoring systems is people don't know necessarily what to do with that information. And this is important. So over time, the recorded values also provide additional information with determining potential problems within the transformer itself. So here's what you're going to look for in a monitor report, and this comes out of a Schweitzer relay. So excessive through fault occurrences within a given period can indicate the need for things such as tree trimming for maintenance and right-of-way clearance. But the report below, this shows the through fault report on the transformer. The report provides a total I squared T value for each phase. Also provides the date, time, the duration of the through fault. Now, in terms of duration, things that can exceed the duration in terms and make that a lot longer, which of course will be more damaging, things like breaker failure, okay, can hold that through fault a lot longer. So the maximum current depends on what type of through fault is occurring, whether it's just a single tree branch that's momentarily there, or whether it's a pretty bad lightning strike. But all this information is provided to you in the through fault report. Now, in terms of diagnostics, investigative tests for through faults, we're going to talk about a couple of these things. Your frequency response, or SFRA, is probably the more common one that we're familiar with to determine mechanical damage in the transformer. The other is short circuits and impedance, or also known as the leakage reactance test. And this comes out of IEEE P57 or PC 57170, which is part of the diagnostics of solid insulation. So we'll talk about two tests to actually look for mechanical damage caused by through faults. And one is, again, SFRA, and the one we're most commonly familiar with in the industry. And then we'll talk also about leakage reactance. Now, your IEEE guide, C57149, is the guide for application and interpretation of SFRA. And that was in 2012. Well, it's just getting ready to be released as a new revision of that, which includes a lot better information in terms of some of your complex transformers, things like zigzag transformers and whatnot. And then the other is C57152, which is the guide for diagnostic field testing of oil-filled power transformers, regulators, and reactors. And that covers the leakage reactance test, as well as many others too. Very valuable guide. So SFRA, sweep frequency response analysis. This is a method that we use to evaluate the mechanical integrity of the core, the windings, the clamping structures within the power transformer itself, by measuring their electrical transfer functions over a wide frequency range. We're looking for things like core movement or faulty core grounds, winding deformation, winding displacements, partial winding collapse, buckling, broken clamping structures, shorted turns, and open windings, and et cetera, et cetera. But basically, the focus is on any mechanical, structural issues with the winding of the transformer itself. And I like to think of an SFRA plot as a fingerprint, because no two are usually identical. Okay. Um, Transformers generate a unique signature when tested at discrete frequencies and plotted on a curve. The distance between the conductors of the transformers, it forms a capacitance. And any movement of the conductors or windings are going to change the capacitance. And it'll show up in the results of these tests when you start doing a comparative analysis. This is why it's so important when you have a new transformer to start with a baseline. And one of the things you want to make sure is that when you do order a new transformer from a manufacturer, make sure before they ship that unit, that at the factory they get a SFRA baseline, because the changes in the frequency response can be compared over time between test objects or within the test objects themselves. Well, let's say that you've had a transformer out there for a long time and nobody ever did an SFRA. Well, you might ask, well, what good is it then? Well, we can do SFRAs and look at the difference between interwindings, okay, to see if there's any difference, because they should be pretty much the same. We can also look at traces from identical transformers that are on the system, but get that baseline, please. Even if you have an older transformer that you haven't done this type of test before. Now, the procedure is for a two winding transformer, delta Y, it's fairly simple. As you get additional windings and you get into things like zigzag transformers, some that are more complex, it can be quite a few tests that you actually have to run. But basically, you have a measurement lead and you have a voltage lead, and it's a low voltage non-intrusive test. Of course, we can also always have to do this offline. We can't do it online. But basically, think of SFRA as a chest X-ray. If you go in to get your chest X-ray, they're going to go from front to back, then they're going to go from back to front, and then they'll go from side to side. They want a good 3D image of anything going on in your lungs. Well, SFRA is kind of the same thing. And here is, and this again comes from C57149, the recommended tests for a two winding DY1. And it tells you, where your reference voltage is going to be. That's where the signal's going out, what your response is going to be, what needs to be shorted, and what needs to be grounded. And there's basically three types of tests that you're going to run. One is called the high voltage open circuit test, where all your other terminals are floating. And then you're going to do a low voltage open circuit test. And then you're going to do a short circuit test, because areas in which you might find abnormalities are going to indicate where that fault might be or what the fault came from. So in these lower frequencies of our SFRA, we're looking at the problems associated with the core of the transformer itself. And the mid-range frequencies, this would indicate a problem in the interaction between the windings. And then in the higher frequencies, we're looking at deformation in the winding structure influences. So the good news is, when you have a piece of equipment like this, it comes with a nice software program, it's going to do the analysis for you. But what we find, winding movement caused by high current faults in a three-phase core form transformer is generally associated with the low voltage winding in the form of radial deformation. So what that tells us, that our diagnostic focus will be given to the low voltage open circuit and high voltage to low voltage circuit responses. And the open circuit documents for both open circuit and high voltage to low voltage short circuit responses, you can see clearly in this figure below. This indicates the measurements during the high current radial deformation. So we can see this clearly in the traces below. So those are the two areas that we want to look for if we're concerned that excessive through faults or a high through fault has created some type of mechanical damage. Okay, so SFRA probably is the most inclusive tool in terms of looking for mechanical damage in the transformer itself. Now, there is another test that is important as well, and this is called the leakage reactance. We used to call this, or still do sometimes refer to this as short circuit impedance. So think of this, okay? Think that you have a wooden trough running downhill, and there's water in that trough. Well, naturally, some of the water will spill out normally, okay? And think of that as flux, some normal flux leaking out of the transformer. Well, let's say you come along and you put a big rock in the middle of the trough. Well, you're going to get a lot more water spilling over, okay? And it's the same principle with leakage flux, okay? Because we're going to have some normal leakage flux in a transformer, okay? And this is measured in terms of the overall impedance of the transformer. So if we have a disruption, okay, in the windings itself, you're going to have more leakage flux, and this is going to be influenced by the impedance that we measure on the transformer. And this is just your simple diagram on how flux through the transformer. And you can see here we have normal leakage flux. Well, if you get any kind of deformation in these windings, that impedance value is certainly going to change when we measure it. Now, what are we comparing it against? Well, your nameplate on the transformer has the impedance stamped right on it, okay? And that is what we're going to use to compare. Now, one thing to keep in mind, okay? When you get a new transformer, whatever the manufacturer measured in terms of the impedance on the de-energized tap changer is going to be that. Now, if you change that de-energized tap changer to another position, that's going to change the impedance. And you have to get a new baseline. So that's very important. The other thing is that you always want to perform leakage reactance test on the neutral tap of an on-load tap changer. So keep those two things in mind. Okay, so the test sequence is going to be in two parts. The one is your three-phase equivalent. And that is where we're doing each phase at a time, but we're combining those together and averaging them out to give us that measured value that should compare to the stamped value in impedance on the transformer. If the other thing we're going to do is we're going to do a per phase test. and we're going to measure the impedance on each one of the three phases individually. And here's your connection diagram. Okay, and this is important to follow: what you need to ground, what you need to short, and where you're going to measure. Okay, now what IEEE tells us is that on a three-phase equivalent, and this is your calculation. The test sets will all do this for you, but you'll enter the actual nameplate, and then it'll take the calculated three-phase impedance and calculate the delta between what you measured and what's on the nameplate. And IEEE standards say that it should be plus or minus 3%. Okay, if it's greater than that, you have a potential problem. Okay. The other thing is that when you do the per phase, okay, what's important to note on the three phase is that it must be within 3% of each of the other two phases. Okay, so if you have, plus or minus 5% on one winding, you know that that particular winding may have an issue. Now, let's take a look at a significant case study here. And this was a transformer on a 50 MVA transformer, configured a DY1, and the differential relay tripped. Okay. And there was some oil that appeared to be leaking from the low voltage de-energized tap changer. So they applied the standard test protocol. Well, the first thing you do, okay, if your differential trips, is you pull an oil sample and you send it off to the lab for evaluation. But in the meantime, we also want to run our basic electrical test to see if we can diagnose why the differential tripped. So this one was done. We ran the power factor test, but also followed with SFRA and leakage reactance. And when we first ran the power factor test, it wouldn't even run at 10 kV. So what do you do when it doesn't run at a higher voltage? Well, you try and lower the voltage. So we lowered it to 7 kV, and the power factor was almost 50%, okay, on the CL insulation. And that is clearly unacceptable. Okay, so now we know we have a problem. We know where the problem is or what caused it. No, not necessarily. Okay, so we get the DGA back. Okay, what's so interesting about a DGA? Now, dissolved gas analysis has to be historical information. You have to have that timeline of gassing values, and that's the most important thing in terms of maintaining records for the DGA. And you'll see here, this is interesting. There's never been an issue with acetylene in this transformer before, but look at it now. I mean, it's absolutely through the roof. Okay, from 0 up to 21. That's a clear indication of we got some extreme heating going on with it within the transformer itself. Now, you can get acetylene from a number of different reasons. Okay, it could be you could have a complete insulation breakdown too, but usually when you have insulation issues, your CO and your CO and your O2 are going to be highly elevated as well. Not necessarily the case here. So this is a clear indication to me. I would interpret it this as, hey, I think we've had a mechanical failure in the windings of the transformer. So when we did the leakage reactance, and this is why it's important to do both three-phase equivalent and per phase, you'll notice here that on our three-phase equivalent, it's within that 3%. The delta is only 2.85. But when we look at the per phase, we clearly see, okay, we've got an issue on phase B. Okay. And this is typical of an open circuit. Your DC winding resistance test also confirmed an open circuit. However, phase A and C produce the expected 40 milliohms. So we know where it's located. Now, if we look at the SFRA results, that indicates a high impedance fault on phase B of the low voltage winding, clearly. So both low voltage open circuit and high voltage to low voltage short circuit tests clearly provide this evidence, and the above trace clearly illustrates that we got a problem on phase B. And you can see the delta between the others. Okay. So when we broke the transformer down, This is what we found. Okay, it's certainly not pretty. And this was, again, attributed to a very high, very significant through fault on the transformer itself. Okay, so I have a surprise for everybody. This is a little bonus portion of the presentation that I want to share with you because it really doesn't have anything to do with mechanical failure, but it's an additional test that you can provide your customers or provide your engineers with when you're doing a leakage reactance test. And we call this frequency response of stray losses, or FRSL, as some people claim. Now, in a leakage reactance, we're evaluating the impedance, both real and reactive components. In frequency response of stray losses, we're only looking at the resistive component of the impedance. Now, leakage reactance, we do at 60 hertz. Frequency response of stray losses, we're going to do at discrete frequency points from 15 up to 400 hertz. And with leakage reactance, we're looking for defects or detects winding deformation. But here we're going to look for a thing called a short-circuited strand or conductor bundle within the transformer on the primary windings. Now, where did this come from? Well, back in 1970, some of the engineers at Hydro-Quebec thought that they could come up with a way to utilize another method of determining mechanical failure. And so they decided that they were going to increase the frequency of their test signal and look at the results in terms of resistance. Well, it really didn't provide them any additional information in terms of, possible mechanical damage. But what they did find out, and this was years later, that if you have a conductor bundle that's compromised in any number of the individual insulated conductor strands, it would cause that measurement to increase, okay, in terms of the impedance. Now, how does this work? Well, um, we basically run this test at the exact same time or just following the leakage reactance test. You have test instruments out there from Megger, from Omicron, from Raytech that all have this little capability. And if you look at, say, primary test manager from Omicron, when you get to the screen that says leakage reactance, there's a little box where you can check that says do frequency response of stray losses, or FRSL. Okay, so what we're going to do is this is part of the per phase test. We're going to do it on all three phases, and we're going to measure the resistance at different frequencies from either 1 hertz or 10 hertz up to 400, depending on which test instrument you're using. Now, the theory of this, and let's look at this real quickly. We all know that current cuts through a conductor. If you DC it, it's on the entire surface of the conductor. As we switch from DC to AC, current's only flowing through an outer portion of that conductor. Okay, and that's what we call the skin effect. Okay, so if we go from DC to 60 hertz AC, the current density is reduced by about 63% of how the current's flowing through that conductor. Well, what does that mean? Well, what causes the skin effect to get worse or more pronounced, which is what we're looking to do here. As we increase the frequency, okay, we're pronouncing the skin effect. And what happens when you pronounce the skin effect to the resistance, the AC resistance? Well, naturally, that's going to rise. Okay. Also, the diameter of the conductor, okay, has an influence on the skin effect and the resistance. So here in the US, and other parts of the world as well, on the primary windings of the transformer, it's not a solid strand. It's a series of conductor bundles with insulation between themselves that are wrapped around the iron core. This one is more typical of what we see in the US. You have these flat conductors with insulation in between. Well, what can happen is that you can have a short in those conductor bundles. And that is going to really pronounce the AC resistance as we go from 1 up to that 400 hertz range. So the higher you get, the more you're going to pronounce this condition. So if we ran a test where we have normal conductor bundles and there's no issues, all three phases should line up by themselves. If we see this, we can clearly see that in the higher frequencies, we have a big discrepancy between A and B phase and C phase. And that would indicate that we have a shorted conductor bundle. And look what's measured here at 60 hertz. You don't see the difference there because we're not pronouncing that skin effect. So what this was a part of C. Gray's Guide for Transformer Maintenance, and this was a working group A2.34, and it defines the failure criterion for frequency responsive stray losses, where the difference in AC resistance between the phases, if it's greater than 15%, you've got a serious problem. However, a problem can actually manifest itself as time goes on between phases. So even if you have a 2 to 3% difference, okay, especially on a brand new transformer, okay, this is something you need to talk to your transformer manufacturing about. So when do we perform frequency responsive stray losses? Well, since this can be related to manufacturing defects, it should be a routine test during the commissioning process because it's unlikely that FRSL is included in a factory acceptance test. I can tell you that virtually nobody does this test, but it also establishes a nice benchmark. You know, if your transformer is showing signs of increased gases such as hydrogen, um, and no other electrical tests, everything seems normal, then I would look at frequency responsive stray losses. Because I'll tell you this right now, there is no other diagnostic test available that can find this condition until it gets too late. And when it gets too late, this is what you're going to find. Overheating and eventual insulation failure due to a shorted conductor bundle. So that's just a little added bonus that I thought I'd throw in. And since you're doing a leakage reactance test and a lot of your modern test equipment have variable frequency voltage in the power supply, I would highly recommend to incorporate and interrogate this as part of your routine testing as well. It doesn't take much time, takes very little time. You won't even notice it because you're already connected to the transformer and running the short circuit impedance either way. Okay, so I think that's about 45 minutes.